This lesson's about energy and energy changes in simple harmonic motion, and here are your objectives. First, let's review some equations that are going to be handy in thinking about energy in simple harmonic motion. We know that the potential energy stored in a spring is equal to half kx squared, where k is the spring constant and x is the displacement from equilibrium. We also have a few relationships for the angular frequency of oscillation. We know that the angular frequency omega squared is equal to k, the spring constant, divided by m, which is the mass of the mass on a spring that's oscillating. And we also know that the angular frequency is equal to 2 pi divided by the period, or 2 pi times the frequency. If we go back to this relationship, we can rearrange this for an expression for k. K is equal to m, the mass of the mass on a spring, multiplied by omega squared. And we've seen two different expressions for the position as a function of time, or the displacement from equilibrium as a function of time, of an oscillating mass on a spring. One where we are starting at an extreme of motion at time is equal to 0, that's this one. And if we start at the equilibrium position, then we would be using a times sine omega t. So we'll use these equations as we go forward. Now, let's take a look at a mass on a spring oscillating backwards and forwards. If we assume that the system is frictionless, so there's no friction between the surfaces here and there's no friction in the spring, then all the energy is going to be conserved. The total energy in this system is going to be a constant. Let's set the equilibrium position here, and we'll imagine the extremes are out here and over here, and I'll try and draw these symmetrically. Now, at the extremes, remember the block is going to come to rest, so the kinetic energy is going to be equal to 0. And as a result, the total energy is just equal to the potential energy, the energy stored in the spring. That's going to be the same at this extreme as well. In the middle here, we have only kinetic energy. So the kinetic energy is the total energy, and there is no potential energy stored in the spring because the spring is at its resting length. So at the edge, the total energy is equal to the potential energy, and therefore the potential energy is at a maximum. And at the equilibrium position, the total energy is equal to the kinetic energy, and so the kinetic energy is at a maximum. So let's ask ourselves, what is this total energy equal to? Let's think about this case here at the extreme, where the total energy is equal to the potential energy. We have this relationship for the energy stored in a spring, the potential energy in a spring, and so the maximal potential energy, what's happening here, is equal to a half times k times whatever the x value, the value of displacement from equilibrium, is here. Well, if this is the 0 point, if that's the equilibrium position, and we're at the extreme, then the displacement is just equal to the amplitude. And so we have a half times k. Instead of x squared, we sub in a for x, and we get a half k a squared. So again, the displacement from equilibrium, x is equal to a here at the extreme. And that would be the same in this direction as well. We'd have x is equal to negative a. So the biggest possible potential energy in this situation is found when x is equal to a, the amplitude, and so we get potential energy max is equal to half times k a squared. Well, that's also got to be equal to the total energy, because the total energy at the edge is just potential energy. And that also means that it's equal to the kinetic energy at the middle, because that's where we had the maximal kinetic energy, and it's equal to the total energy there as well. So this relationship, this expression, half times k times the amplitude squared, gives us the total energy, it gives us the maximum potential energy here at the extreme, and it gives us the maximum kinetic energy here at the equilibrium position. Now we can think of all of this on a graph of energy versus displacement from equilibrium. I'm going to mark the equilibrium position here, and then I'm going to mark the extremes. This is x is equal to a, and this is x is equal to negative a. And we've seen now that we need a total energy equal to a half times ka squared. A is not a variable. Once you set this thing oscillating with a particular amplitude, if there's no friction, the amplitude is going to stay the same. So there's no variables here anymore, and that's a constant. So here's our total energy, and it's a constant. It doesn't vary with displacement from equilibrium, and it's going to be equal to half times ka squared. However, our potential energy has a variable in it. Our potential energy is equal to half times kx squared, and x is varying. It's getting more positive in this direction and more negative in this direction. But this is a parabola as a function of x, and so we need to draw a parabola for that. So I'm going to use red here and draw myself a parabola that's upward facing. So this is my potential energy. My potential energy equal to a half kx squared. Now, if the potential and kinetic energies always need to sum to this total, then we just need to draw an upside down version of that for the kinetic energy. So I have an upside down parabola, and this is my kinetic energy, maximum at the middle here, taking on the value a half Ka squared. So this is a graph of energy versus displacement from equilibrium for an object undergoing simple harmonic motion. So once again, the total energy is equal to the kinetic energy plus the potential energy, and we know that the kinetic energy is equal to a half times mass times velocity squared, and we know that the potential energy stored in a spring is equal to a half times kx squared, and now we've seen that those two must add up to a half times ka squared. So let's summarize all of this down here. Energy as a function of displacement from equilibrium, we've seen that the total energy is a half Ka squared. Now that's not really a function of displacement, but we're going to use that momentarily. Also, we have seen above that you can replace K by m times omega squared. So this could equally well be written as a half times m times omega squared a squared. That's another expression for our total energy. And our potential energy, which is a half times kx squared, again, be careful, a is not a variable anymore. The amplitude is set once it's in motion, but x is going to change as it slides back and forth. The potential energy, which is changing, is going to be equal to a half times kx squared. And using the same substitution of m omega squared for k, I could write this as m times omega squared times x squared. And if I want to find the kinetic energy, I just take the total energy and I subtract whatever energy is made up by potential energy, because those kinetic and potential are the only two types of energy we have here. So I take my half times Ka squared and I subtract a half Kx squared. And I can factor out the half K and get a half K times a squared minus x squared. And once again, if I prefer to write K as m times omega squared, I can do that. So m times omega squared times a squared minus x squared. And so this gives us a way now of figuring out the energy if we know the position, and vice versa. So let's say we had a given system oscillating and we wanted to know how much energy is kinetic and how much is potential. When you're 4 centimeters away from the equilibrium position, these equations would let us do that. And just taking a step back to look at this more generally now, we saw that the total energy was equal to a half times Ka squared. So the total energy of a harmonic oscillator is proportional to the square of the amplitude of oscillation. The total energy is proportional to the square of the amplitude. If you double the amplitude, you are quadrupling the total energy stored, and as we've seen, that energy is going to get swapped back and forth between kinetic and potential energy. We can also use those equations to solve for the velocity at a given displacement from equilibrium. So we know that kinetic energy is equal to a half times mv squared. We've also now seen that it's equal to a half times m times omega squared times a, the amplitude squared, minus x squared, x being the displacement from equilibrium. And we can cancel out the half m and square root both sides, and we get that the velocity is equal to plus or minus omega times the square root of a squared minus x squared. So again, a is the amplitude, it's not a variable anymore, neither is the angular frequency once we know the parameters of the system, k and m, and so the only variable here is x. We plug in the displacement from equilibrium and it's going to give us the velocity. Okay, so everything above has been looking at energy as a function of position or displacement from equilibrium. Now let's look at it as a function of time. And we're going to assume that we are starting from an extreme. So if we're starting from an extreme, then we're going to use x as a function of time is equal to a times cos of omega t. Again, we are starting from an extreme. when time is equal to 0. If we were starting from equilibrium, then we would use the sine version of this. And you'd get a very similar relationship as to the one we're going to see in a moment. So the potential energy we've seen is equal to 1/2 times k x squared, where x is the displacement from equilibrium. But x is equal to a cos omega t. So I can replace that. So I get 1/2 times k a cos omega t all squared. And that is equal to 1/2 times k a squared times cos squared of omega t. This, of course, is our total energy. So that's our total energy. And now we've got this cos squared function. And if we want to find the kinetic energy, again, we just take the total energy, so 1/2 times k a squared, and we subtract the potential energy, 1/2 times k a squared times cos squared omega t. Okay, so those look complicated, but just understanding that they are cos squared graphs is going to help us understand the graph of energy as a function of time. So here, graphed on Desmos, are two graphs. In blue, we see a cosine x graph, and in red, we see a cosine squared x graph. And I want you to notice a couple of things. First of all, the regular cosine x graph oscillates between +1 and -1, and the cosine squared x graph only goes between 1 and 0. The output of this equation can only be positive because it's squared. So it's going between 1 and 0, it's never negative. Also notice that the period of the cosine squared x graph is half as long as the period of the cosine x graph. Bringing that back to our energy time graph, we know that we have a total energy that's equal to 1/2 times k times a squared, and that's going to be made up of a shifting proportion of the two energies, potential and kinetic. If we have started from an extreme of motion, then our potential energy, which I'm going to draw in red, starts at a maximum. Now this time is going to be fractions of a period of oscillation. So this is the full period, this is 3/4 of the period, half a period, and 1/4 of the period of the actual thing oscillating backwards and forwards. Here it's ended up back where it started. So now we need a cos squared graph for our potential energy. And that's going to look like this. Remember, again, it's got half the period of the underlying oscillation. And now here in green, I've drawn the kinetic energy, also a cosine squared shape. Lastly, let's just remember that the period of the energy change is half as long as the period of the oscillation. So that's an introduction to energy and energy changes in simple harmonic motion.